Earth, landscapes have changed, continents have drifted, and oceans have filled voids. While mountain ranges have risen and crumbled, water has carved valleys and canyons, creating unique ecosystems. This was a time when life was just beginning to awaken on the planet, but humanity only appeared on this stage at the very end of this grand spectacle. We, humans, are relatively young compared to the age of our planet, like novices entering a long-established play. While Earth has held within itself billions of years of evolution and change, we are but a drop in this ocean of time. And here, on this tiny line of time, amidst millions of years when the world was inhabited by creatures of which we can only speculate, we began to leave our mark. This mark is not just a record in history, but an attempt to understand and grasp our place in such a vast and ancient context. We stand at the crossroads of time, where the seemingly insignificant appearance of Homo sapiens becomes a significant event, and its culture and achievements, from art to technology, begin to shape the world around us. In this context, it is worth considering what role we play in this long history and how our actions influence the future of a planet that still remembers times when life was just beginning to break through stone and water. For instance, over the past decades, we have witnessed significant changes in the climate, which underscores not only the fragility of our civilization, but also the importance of studying past epochs to better understand how to coexist with our environment. Understanding the history of Earth and its changes can provide us with keys to survival and adaptation in conditions where humanity faces new challenges born of both natural processes and human activity. This process was not rapid. Billions of years were needed to create conditions conducive to life. In these long periods of time, opportunities for the emergence of intelligence were laid. Nevertheless, it was in these conditions, under the influence of chance and laws, that the first forms of life could arise, which later evolved into complex organisms. This intelligence, as a result of billions of years of evolution, became possible only due to this endless dance of destruction and creation that took place on Earth. The concept of deep time helps us grasp the scale of Earth's history by representing it as a geological timeline. For instance, the emergence of the first multicellular organisms occurred around 500 million years ago, roughly corresponding to 5 in the morning. Dinosaurs, who ruled the planet for over 160 million years, appeared around 10 in the morning and disappeared by 1 in the afternoon. Humanity, as a species, emerged only in the final seconds before midnight, approximately 300,000 years ago. This means, on this scale, even writing, which emerged around 5,000 years ago, appears in the last minutes before midnight. Thus, this perspective allows us to understand how insignificant our actions are in the context of planetary history. We see that humanity is but a fleeting moment in this endless temporal flow, while Earth has experienced millions of years of change, catastrophes, and evolution. In this context, each hour, each minute, and each second becomes significant not only for understanding our place in the world, but also for recognizing our responsibility for the future of the planet. The Fermi paradox is a philosophical question that presents a remarkable contradiction. If the universe contains so many stars and planets suitable for life, why have we not yet found any evidence of intelligent life? This paradox challenges our assumptions about the likelihood of extraterrestrial civilizations, as the number of potential worlds where life could develop is astronomical. Our galaxy, the Milky Way, alone contains more than 100 billion stars, many of which have planets within the so-called habitable zone, where conditions could be suitable for life. Despite the efforts of astronomers and scientists, from radio signals to exoplanet exploration, we have not found even a hint of the existence of other intelligent life. This raises numerous questions. Perhaps intelligent beings exist, but are too far away for their signals to reach us. or maybe they exist but have no desire or ability to communicate with us. Some theories suggest that highly advanced civilizations may face self-destructive factors before they can reach a stage where they could be detected. Others propose that we simply do not understand how to recognize their signals, as they might use technologies different from ours. This enigma of extraterrestrial life and its apparent absence amidst countless star systems opens up many avenues for thought and research, but it remains without a definitive answer. If we were to discover even one signal, it would fundamentally change our perception of the cosmos and our place within it. Silurian Hypothesis, proposed by scientists Gavin Schmidt and Adam Frank, poses a provocative question. Could there have been a technological civilization on Earth long before the appearance of Homo sapiens? These researchers argue that there were periods in Earth's history when conditions could have favored the development of intelligent life capable of creating technologies. For instance, around 400 million years ago during the Silurian period, Earth was covered with dense forests and the oceans teemed with diverse forms of life. Schmidt and Frank analyze climatic and geological data to determine if such conditions could have led to the emergence of a highly advanced civilization. They suggest that if such a civilization had existed, traces of its activity could have been lost due to tectonic processes or climatic changes that inevitably altered the planet's appearance. The civilization might not have left behind artifacts that we could discover today, as it could have existed for a relatively short period before disappearing. In their view, this is not just a fantasy but a real possibility that warrants further investigation. Moreover, this hypothesis forces us to rethink our understanding of time and evolution, considering the existence of technological civilizations within the context of Earth's billions-year history. The research by Schmidt and Frank raises important questions about how we can identify and recognize civilizations that may have existed in the past and what their achievements might have been. In this context, it becomes clear that studying such hypotheses requires not only a scientific approach but also philosophical reflections on humanity's place in the historical context of Earth. Geological processes are a set of natural phenomena that shape and alter the Earth's surface. These processes can act over millions of years, shifting layers of Earth, changing the landscape, and modifying climatic conditions. They can have a significant impact on the existence and development of civilizations, sometimes erasing all traces of their existence. Throughout history, when civilizations reached their peak, geological changes could occur imperceptibly, undermining the foundations of their cultures and leaving only fleeting reminders of once thriving societies. Often such changes occur as a result of natural disasters that can cause widespread destruction, but even less noticeable processes can accumulate destructive power, gradually flooding cities or burying them under the earth. This leads to many of the achievements of ancient peoples being hidden beneath layers of earth and time. As a result, our ability to restore a complete picture of historical heritage is limited, as many artifacts either disappear entirely or are preserved in a fragmented state. The inability to see the full diversity of ancient cultures and their interactions with the surrounding environment creates a need for a deeper understanding not only of human history, but also of the mechanisms that influence its preservation. This leads us to crucial questions about how these processes interact with cultural heritage and how they affect our perception of the past. Geological changes can not only erase physical traces, but also distort our understanding of historical events, as we often base our knowledge on what remains after these processes. For example, what we see today may be only a shadow of what existed before, and this requires careful analysis and the use of modern technologies to study the layers beneath the Earth to uncover information about the civilizations that have been lost to time. It is important to note that each discovery can change our understanding of the past and advance science, opening new horizons for research. For instance, the use of georadars and other methods allows us to find the remains of structures that have long been lost, but can still tell us about the lives of our ancestors. Erosion is a powerful geological process that, over millions of years, can destroy even the most impressive structures left by ancient civilizations. It occurs due to the influence of various factors such as water, wind, and temperature changes. Water, penetrating cracks in rocks, freezes and expands, leading to the destruction of the material. Wind, in turn, carries particles of sand and other minerals which can scrape the surface of rocks, gradually wearing them down. Additionally, chemical reactions occurring on the surface can convert metal into oxides, weakening the structures and making them vulnerable to further destruction. For instance, it is important to note that erosion does not always occur uniformly. Depending on climatic conditions and location, different parts of structures may be destroyed at different rates, creating unique forms and landscapes. Thus, over the course of thousands of years, nature actively transforms the face of the Earth, depriving us of the traces of former civilizations and leaving only hints of their greatness. Scientific research shows that even modern technologies and methods of erosion protection cannot completely stop this process, and over time, any structure, no matter how monumental, is subject to destruction. Tectonic movements of the Earth's crust represent one of the most powerful and destructive processes on the planet. Continental plates, which make up the surface of the Earth, are constantly in motion, colliding, diverging, and subducting beneath each other. When two plates collide, a powerful pressure is generated, which can lead to the formation of mountain ranges, such as the Himalayas, which resulted from the collision of the Indian and Eurasian plates. This process can also cause earthquakes that can destroy cities and erase the traces of civilizations, leaving only ruins behind. Conversely, when plates diverge, as in the case of the Mid-Atlantic Ridge, new oceanic floors are formed, but at the same time, old continents can sink, carrying any archaeological finds and traces of human activity into the mantle. Subduction. The process of one plate descending beneath another also leads to the formation of deep oceanic trenches and active volcanic activity. For instance, in the region of the Pacific Ring of Fire, where an oceanic plate descends under a continental plate, there are powerful volcanic eruptions and earthquakes that can wipe out entire civilizations from the face of the Earth. These tectonic processes are not just disasters, they create and destroy, shaping our planet and altering its appearance. As a result, many ancient cities and monuments which were once centers of culture and civilization end up buried under layers of earth or submerged in the ocean, becoming invisible to future generations. The process of sediment accumulation is a crucial component in the formation of Earth's geological structure. When rivers, lakes, or oceans flood land areas, they carry with them particles of soil, sand, and other materials. Over millions of years, under the influence of water pressure and new layers, sediments begin to compress, transforming into sedimentary rocks such as sandstone, limestone, or clay. This process can take millions of years, resulting in the formation of thick layers of rock that can bury ancient structures and artifacts. These layers not only conceal traces of human activity, but also preserve information about climate changes, flora and fauna of those eras. Additionally, such sedimentary rocks can contain valuable minerals that later become the subject of mining. For instance, coal and oil are formed from organic remains that also accumulated in water bodies and were buried under layers of sediments. This process of accumulation and compression creates conditions for the formation of entire geological layers that can be studied to understand the history of Earth and the evolution of life on it. After millions of years, when tectonic processes bring these layers to the surface, researchers can discover temporal capsules that reveal information about the life and nature that existed in the distant past. Temporal windows represent unique periods in history when certain conditions on the planet facilitated the rapid development of civilizations. These for example, in some parts of the world, prosperity and decline can occur simultaneously. This creates a complex picture of civilization development, where some peoples rise while others face crises. Such dynamic processes demonstrate how invisible threads of time connect the fates of peoples and cultures, and how even minor changes in living conditions can lead to global changes. In this context, the study of temporal windows allows for a deeper understanding of why some societies achieve success while others remain in the shadows. This understanding opens new horizons for research, enabling the analysis of the influence of various factors on historical development. For example, in some temporal windows, urban growth and trade development are observed, while in others, migration and the collapse of entire empires occur, fundamentally altering cultural and social landscapes. As a result, in this context, clear evidence of such changes can be found in archaeological findings, which testify to the change of cultural layers and changes in material culture. The Silurian period, which spanned from 443 to 419 million years ago, was a pivotal stage in Earth's history when climatic conditions became favorable for the development of complex life forms. The climate was warm and humid, which promoted the growth of reefs and marine ecosystems. The oceans teemed with life, with early fish and corals building massive reefs, as well as various mollusks and trilobites that dominated the marine environment. On land, these conditions created ideal prerequisites for the emergence and evolution of more complex life forms that could adapt to various ecosystems, both in water and on land. The appearance of the first terrestrial plants and the diversity of marine life indicate that life not only survived but also actively developed, creating numerous new niches and ecosystems. These geographical and ecological changes provided additional opportunities for adaptation and diversification of life. Consider the Carboniferous period, which spanned from 359 to 299 million years ago, was an era when Earth's atmosphere reached an unprecedented level of oxygen, approximately 30%. This created ideal conditions for the flourishing of diverse plants and animals. Lush forests composed of giant ferns, conifers, and other primitive flora covered extensive territories, forming vast ecosystems. These forests laid the foundation for the accumulation of significant amounts of coal, which formed as a result of the decomposition of vegetation in swamps. Additionally, in the marine waters, ancient fish such as stegocentrics and sharks dominated, exhibiting significant increases in size and diversity compared to previous eras. These conditions fostered the creation of complex food chains and the expansion of biomes, thereby contributing to the further development of life on the planet. By the end of the Carboniferous period, the first understanding of ecosystems as complex interactions between organisms and their environment began to emerge. A significant achievement of this time was also the development of the first seed plants, which provided new methods of reproduction and adaptation to changing conditions. During this period also saw the emergence of the first insects, such as dragonflies, some of which had wingspans of up to 30 centimeters. Terrestrial ecosystems were so advanced that they supported complex food chains and interactions between species. In some regions, large limestone formations existed, which could have served as sources of useful minerals for future civilizations. During this time, there was also significant plate tectonic activity, which could have influenced the climate and ecosystems in the future. Ultimately, the combination of all these factors created unique conditions that could have sustained life at a very high level, had it not been for the growing threat that was already looming on the horizon. Throughout these, mass extinctions occurred in various historical epochs, leaving behind voids that were subsequently filled with new forms of life. The Great Extinctions differed from isolated incidents. Rather, they were global processes that affected the climate, ecosystems, and geological activity of the planet. These events were often characterized by a sudden deterioration of living conditions, leading to the demise not only of individual species but entire ecosystems. These catastrophes paved the way for new species, whose evolution occurred in conditions that had not previously existed on Earth. For instance, after each such extinction, life on the planet was restored, but in a modified form with new, dominant groups of organisms. This creates a striking picture of how life on Earth can adapt and change in response to external threats. Some scientists believe that such events may be linked to natural catastrophes, while others point to the influence of human activity on the contemporary ecological situation. Each time a mass extinction occurred, it provided an opportunity for new forms of life to emerge, which could later occupy the niches left by the vanished species. It is important to understand that these processes continue to influence the evolution and diversity of life on Earth even today. This event fundamentally altered Earth's ecosystems and served as a reset for evolution. Scientists attribute several causes to this catastrophic outcome. One of the most volcanic eruptions released enormous amounts of carbon dioxide into the atmosphere, leading to global warming and changes in the chemical composition of the oceans. Simultaneously, large reptiles and amphibians on land also went extinct, creating new ecological niches for other species. Since the Permian extinction acted as a catalyst for the emergence of new life forms, including the first dinosaurs and the ancestors of mammals, which would later shape the Earth's biosphere for millions of years. This event marked the beginning of a new evolutionary stage that led to the diversity of life forms we are familiar with today. A crucial aspect of this process was the recovery of ecosystems, which took millions of years. Scientists note that while the Permian extinction was a catastrophic event, it also opened the door to new biological diversity, demonstrating how life on Earth can adapt to the most extreme conditions. By the end of the Triassic period, which followed the Permian extinction, Earth's ecosystems had significantly changed, and new species emerged to dominate various ecological niches. The Cretaceous-Paleogene extinction event occurred 66 million years ago and was one of the most catastrophic events in Earth's history. This event led to the disappearance of approximately 70% of all living species, including dinosaurs, which had dominated the planet for over 100 million years. Scientific research indicates that the primary cause of this extinction was the impact of an asteroid with a diameter of around 10 kilometers in the vicinity of the modern Yucatan Peninsula in Mexico. The surface temperature of Earth dropped dramatically, causing the death of plants and subsequently the extinction of herbivorous animals, followed by carnivores. It is intriguing to consider that if highly developed civilizations had existed at that time, they too could have faced total annihilation, as the ecological catastrophe would have affected all aspects of life, from agriculture to medicine. This period marked the beginning of the evolution of mammals, which quickly filled the vacant niches and began to develop. In the Chicxulub crater formed by the impact, scientists have found evidence of this event, including rare minerals that form only under high pressures, similar to those generated by an asteroid impact. These geological markers are specific layers or samples within the Earth's geological structure that can indicate various past events and processes. They can be the result of natural phenomena, such as volcanic activity or climate changes, but they can also suggest the presence of a technological civilization. These markers typically contain traces of human activity that leave distinctive changes in the environment. For instance, these could be changes in soil composition, the presence of certain chemical elements, or even specific landforms resulting from construction activities. For example, the study of geological markers opens up a wide range of possibilities for investigating the interaction between humans and nature, and can shed light on aspects such as the level of technological development, social structures, and even cultural practices. It is important to note that such markers are not always easy to interpret, and their analysis requires a comprehensive approach involving various scientific disciplines. Some geological layers contain unusual concentrations of rare metals, which may serve as potential evidence of ancient mining and processing of resources by intelligent beings. For instance, in some places in South America, anomalous levels of gold and silver have been found in layers dating back thousands of years. This raises questions about whether local cultures were actively mining these metals. In Peru, geologists have discovered areas with high concentrations of copper and tin, which may indicate the presence of ancient metallurgical industries. Similar findings have been registered in the Middle East, where in layers dating to the Bronze Age, scientists have found high concentrations of lead and zinc, which also suggest the existence of advanced metalworking technologies. It is important to note that such anomalies may indicate not only mining, but also complex trade routes that may have existed between ancient civilizations, highlighting their economic activity. These studies show that the Earth holds many secrets about our past, and each discovery can open a new chapter in human history. In this context, it is worth mentioning that in some regions, such as Central Asia, high iron content in layers may indicate that ancient peoples used local resources to make tools which would have changed their way of life and social structure. Anomalies in the isotopic composition of ancient rocks present scientists with fascinating mysteries that challenge traditional views on the evolution of life and technology. For instance, in layers dating back over 200 million years, abnormal ratios of carbon and oxygen isotopes have been found. This could indicate that processes on Earth were different from the known biochemical cycles. One theory specific. Furthermore, in some samples, the isotopic composition of strontium and potassium also deviates from the norm. This challenges conventional notions that high-tech processes did not occur on the planet before the advent of humans. Some researchers propose that these anomalies could have been caused by the impact of powerful geological processes, such as collisions with large comets or asteroids, which could also have influenced the isotopic composition of rocks. These new data, for example, findings in mineral-rich areas show that ancient organisms could develop unique mechanisms for processing these elements, opening new avenues for the study of biodiversity. Archaeologists and geologists continue to investigate these anomalies, moving closer to a more precise understanding of the processes that may have occurred millions of years ago. For instance, scientists suggest that this could be linked to the activities of vanished civilizations that employ technologies akin to our modern ones. In some cases, remnants of synthetic substances like polychlorinated biphenyls are found, which were only mass-produced in the 20th century. This discovery raises numerous questions. Could ancient cultures, such as the Incas or Mayans, develop technologies that led to global environmental pollution? Incorporating such data into research could alter our understanding of the interaction between humans and nature over millennia. For example, even if these civilizations disappeared, their ecological impacts could have been preserved in the geological record. The discovery of such traces forces us to re-evaluate our understanding of ancient societies and their influence on the environment. Research scientists are working on analyzing these samples to determine the specific technology used by ancient peoples and how it might have affected the ecosystems of the time. Archaeological search methods are constrained by the temporal limits within which traces of human activity are preserved. Traces of civilizations that existed tens or hundreds of millions of years ago often disappear under the influence of geological processes such as erosion, tectonic plate movements, and climate change. Consequently, many artifacts do not survive to our time or are found in a state that does not allow for their identification. Furthermore, changes in soil composition and the influence of vegetation can obscure findings that could provide insights into ancient cultures. Therefore, findings related to ancient civilizations must be carefully examined and analyzed to confirm their authenticity and their connection to specific historical contexts. Fossilization is a rare phenomenon where organic remains transform into fossils. The main conditions for fossilization include rapid burial of the organism in sedimentary layers and the absence of oxygen, which prevents decomposition. For example, When a fish dies and falls to the bottom of a body of water, its chances of fossilization increase if it is quickly buried by silt or sand, protecting it from predators and bacteria. However, for instance, climatic conditions, soil acidity levels, and even the chemical composition of water can significantly affect the likelihood of preserving remains. Furthermore, to date, there are only a few known cases where the remains of ancestral humans have been fossilized, indicating the rarity of such finds in the history of our planet. The process of metamorphism of rocks is a remarkable transformation that occurs under the influence of high temperatures and pressure in the deep layers of the Earth. For example, this transformation does not merely alter the appearance of the rock, but also completely erases any traces of processing or use that intelligent beings might have left. High temperatures, reaching several hundred degrees Celsius, combined with pressures exceeding several thousand atmospheres, create conditions in which minerals can recrystallize, forming new minerals such as mica or quartz. Thus, even if ancient civilizations used these stones for construction or other purposes, their traces can be obliterated beyond recognition. For instance, granite, which was frequently used in ancient construction, can lose its original characteristics under the influence of metamorphism, transforming into more complex rocks such as gneiss. In this context, it is important to note that metamorphism not only changes the rocks, but also creates new ecosystems, as some minerals become sources of nutrients for living organisms. The process of subduction is one of the most powerful geological phenomena occurring at the boundaries of tectonic plates. Oceanic crust, unlike continental crust, is denser and thinner, making it susceptible to being subducted under the lighter continental crust. When this happens, the oceanic crust slowly slides into the Earth's mantle, reaching depths of several hundred kilometers. During subduction, not only is this crust melted, but numerous materials, including any evidence of civilizations that once existed on submerged continents, are carried away. For instance, traces of ancient cities and artifacts that could shed light on the history of lost cultures disappear into the Earth's interior, forever hidden from our view. For example, in Japan, where the oceanic plate of the Philippine Sea is being subducted under the continental plate of Eurasia, high volcanoes like Mount Fuji are formed, which have become symbols of the country. Alternate human or primate evolution. Research these aspects of intelligence may also include collective forms of thought, where a group acts as a single entity, making decisions based on shared instincts and sensations. Notably, scientific literature discusses the possibility of forms of intelligence based on principles different from carbon-based life, opening new horizons in understanding intelligence. For example, hypothetical silicon-based life forms might possess cognitive abilities entirely different from what we can currently imagine. This topic generates much debate among scientists and philosophers as it challenges traditional notions of intelligence and cognition. The reptiles, as a group, have existed on Earth for more than 150 million years and have survived numerous ecological changes, which attests to their evolutionary success. Specifically, troodontids, such as Troodon, stand out among other dinosaurs due to their relatively large brains, which in relation to their body mass could be compared to the brains of modern birds. These dinosaurs possessed well-developed sensory systems and likely exhibited certain signs of social interactions, which could also have contributed to their intellectual abilities. An important aspect is that troodontids had unique anatomical features, such as complex tooth structures, which suggests they could adapt to a varied diet. This opens up the possibility of discussing their behavior, as a more diverse diet often requires more complex cognitive skills for foraging and obtaining food. Additionally, this raises the question of how such physical characteristics could have influenced their behavior and level of intelligence. Some studies of their brain structure show that they had areas responsible for processing information and learning, which may indicate the presence of a rudimentary form of intelligence. Such features as a large brain relative to body size may suggest high capacities for learning and adaptation, which in turn challenges traditional views of reptiles as primitive creatures. It is interesting to note that even in modern birds, which are descendants of dinosaurs, there are remarkable levels of intelligence and complex behavior, which may indicate that certain aspects of intelligence in dinosaurs were already present in the distant past. Their evolutionary history, therefore, raises many questions about the possibilities of intelligence that could have existed in these remarkable creatures. It is important to remember that all information about troodontids is based on available fossils and comparative analysis with modern species, making the study of their intelligence increasingly relevant and intriguing. The potential for intelligence in cephalopods, particularly octopuses, has sparked significant interest among scientists. Octopuses possess a complex nervous system with over 15,000 neurons, many of which are concentrated in their arms. This allows them to perform remarkable feats such as opening jars or using coconuts as shelter. Research has shown that octopuses are capable of learning. In one experiment, they learned to open containers with food after several attempts. Octopus for example, study science. There are numerous theories about how their intelligence might have evolved in their natural habitat, making their study particularly important for understanding the evolution of intelligence in the animal world. In such conditions, their learning abilities and tool use could become crucial elements of their survival. Arthropods, particularly social insects, possess remarkable evolutionary potential that opens up possibilities we haven't even imagined. These creatures, such as ants and bees, exhibit extraordinary abilities in organization and cooperation. For instance, ants can create complex colonies consisting of millions of individuals that efficiently interact with each other. This is not merely mechanical cooperation, but rather a form of collective intelligence where information is exchanged between individuals, allowing the colony to adapt to changes in its environment. Bees, on the other hand, build hives with remarkable architecture using wax combs, which are not only examples of engineering skill but also efficient resource use. These hives can reach significant sizes and include complex structures that provide optimal conditions for the life and work of the community. Such levels of organization and architectural creativity raise questions about whether we can consider these creatures as predecessors of more complex forms of intelligence and social structure. These facts underscore that the evolutionary path of arthropods is not only fascinating, but also has far-reaching implications for our understanding of intelligence and social organization in nature. In this context, research focused on studying communication and interaction within such colonies becomes particularly relevant. For instance, in conditions of limited resources or specific climatic changes, organisms can develop similar morphological or physiological characteristics that aid their survival and thriving. Convergent evolution emphasizes the universality of evolutionary mechanisms, where even different paths can lead to the same outcome. This concept is crucial for understanding how Earth's biodiversity is formed and changes. It is worth noting that such adaptations are often driven solely by the necessity of survival in particular conditions, which in turn opens new avenues for studying biological processes and interactions within ecosystems. Scientific research on convergent evolution can also shed light on the mechanisms that govern species change over millions of years. A striking example of this is the evolution of the eye in vertebrates and cephalopod mollusks. Despite being separated by millions of years of evolution, their eyes share many similarities in structure and function. Meanwhile, for instance, cephalopod mollusks lack the color sensitivity found in vertebrates, but possess exceptional abilities to perceive contrasts and movements. Furthermore, the study of eyes in vertebrates and cephalopods offers a unique window into understanding how complex organs can develop in response to similar ecological pressures. Specific eyes as organs of vision serve not only for perceiving the environment but also as a crucial element in the survival and reproduction of species, making their study particularly relevant for understanding evolution. Scientists continue to explore various aspects of these organs, opening new horizons in the fields of biology and evolutionary theory. For example, analyzing the structure of the retina in cephalopod mollusks can lead to new discoveries in optics and the understanding of light. Meanwhile, studying the eyes of vertebrates provides evidence for theories on how various species have adapted to their habitats over millions of years. Convergent evolution of echolocation in bats and cetaceans provides a remarkable example of how similar ecological conditions can lead to the development of analogous sensory systems in entirely different groups of animals. Bats living in dark caves or dense forests have evolved the ability to emit ultrasound signals. These sounds bounce off objects and return to the bat, allowing it to determine the distance to obstacles and the location of prey. For instance, considering that dolphins can use sounds with frequencies up to 130 kHz, their echolocation is a highly developed system capable of adapting to various conditions in the marine environment. Both of these examples demonstrate how animals occupying similar ecological niches can independently develop complex perception mechanisms, highlighting the universality of adaptive strategies in the animal kingdom. It is intriguing that these mechanisms, despite differences in habitat and biology, operate based on the same physical principles of sound waves and their reflection. Convert these two, for example, corvids like crows and jays are capable of solving complex tasks using tools, which was previously considered a unique trait of humans and some primates. In experiments, crows demonstrate the ability to use sticks to extract food from hard-to-reach places, indicating a high degree of planning and foresight. On the other hand, primates such as chimpanzees and orangutans also exhibit outstanding skills in solving tasks that require logical thinking and understanding of cause and effect relationships. Evolution of intelligence in these groups occurred in response to different ecological challenges. Primates adapted to life in complex forest ecosystems, where finding food and avoiding predators was necessary, while corvids, living in open spaces, developed skills to find and use resources more effectively. This shows that high cognitive abilities can arise independently in different taxonomic groups. Research shows that not only morphological or physiological characteristics determine success in survival, but also intellectual abilities. It is important to note that characteristics such as social structure and way of life also play a key role in the development of intelligence. For example, in primate groups where social interactions are complex, a higher level of cognitive skills is observed than in solitary species. Thus, we see how different ecosystems and social conditions shape the intellectual abilities of animals, serving as a clear example of convergent evolution. As a result, such groups as primates and corvids become bright examples of how intelligence can develop in various forms and conditions. Research shows that in some cases, corvids are able to perform tasks at a level comparable to children in early school years, which challenges traditional views that high intelligence is an exclusive trait of mammals. The concept of technological singularity refers to a point in time when the rapid advancement of technology reaches a level of complexity that becomes practically unpredictable for humanity. This phenomenon is driven by the fact that each new technological breakthrough opens doors to further innovations, creating a snowball effect. As a result, changes occur at such a rapid pace that society struggles to adapt, and old models of understanding the world begin to lose their relevance. Technological singularity not only implies an increase in productivity and efficiency, but also radical shifts in lifestyle, economy, and social structure. This state can be compared to the moment when the automobile engine replaces horses on the roads. Initially, everyone adapts to the new conditions, but over time, completely new concepts of transportation and even urban planning emerge. Consequently, changes affect not only the technological sphere, but also cultural, social, and economic aspects of life. During this, it is important to note that this process is not always smooth. Many societies may face difficulties in adaptation, while others may use new technologies to improve the quality of life. This creates an uneven distribution of benefits, which can lead to social conflicts and changes in political structures. Ultimately, singularity poses a challenge to existing institutions and management systems, requiring them to be flexible and capable of rapid response to changes. In this context, there is a need for new approaches to education to prepare future generations for a world where the pace of change will be so rapid that traditional methods of learning may prove insufficient. Against this backdrop, it is crucial to closely monitor how different societies respond to the challenges posed by this new era. Exponential growth of technology in human civilization can be traced from the first stone tools, created around 2.5 million years ago, to space flights, achieved in just a few thousand years. Early tools, such as hand axes and scrapers, allowed our ancestors to effectively hunt and process food. Around 30,000 years ago, more complex tools, including bows and arrows, emerged, significantly increasing the chances of survival. The transition to agriculture, which occurred approximately 10,000 years ago, was a true breakthrough. People began to live settled lives, changing not only their way of life but also their social structures. The invention of writing in Mesopotamia around 5,000 years ago marked the beginning of a new era. Information began to be recorded, which sparked the development of science and technology. The Industrial Revolution of the 18th century led to mechanization of production and mass production, with electricity and steam engines becoming the main drivers of progress. In the 20th century, technology developed at an unprecedented pace, from the first airplanes to spacecraft that sent a human to the moon in 1969. This leap in technological development raises the question of whether similar processes could have occurred with other intelligent species in our universe. Perhaps such an approach to understanding the evolution of technology can lead to new discoveries in the fields of astrobiology and philosophy. For example, research into such possibilities may open new horizons for understanding not only our place in the universe, but also how we can use our experience to drive further progress. How exactly this happens depends on many factors, including climatic conditions, resource availability, and interaction with other species. Technological progress, as history shows, knows no bounds. It moves forward, and its dynamics can be both rapid and slow at certain stages. Throughout history, there have been societies that achieved significant scientific and technological advancements, but also faced internal conflicts and ecological disasters, leading to their decline and disappearance. Another example is the Roman Empire, which boasted remarkable engineering feats, such as aqueducts and roads, but internal political strife and economic issues led to its fall. In both cases, civilizations at the peak of technological progress were unable to overcome the challenges that resulted from their own success. Therefore, understanding the technological horizon is crucial for analyzing the future of any developing culture. Scientific research indicates that the more a civilization relies on its technologies, the more vulnerable it becomes to both internal and external threats. Archaeological visibility is a concept that describes how various materials and technologies used by ancient cultures affect how we can study and perceive them through the lens of archaeology. This understanding is tied to the fact that some materials are better preserved than others, which directly influences the quantity of finds and their condition. For instance, how buildings were constructed, how everyday items were used, or what technologies were employed in production processes will determine what survives to be studied in the future. Therefore, studying archaeological visibility helps us understand how different cultures adapted to their environment and how their technologies influence their survival and development. Additionally, this concept raises questions about which aspects of material culture may be lost due to natural degradation or human activity, potentially leading to a distorted perception of historical processes. This dynamism forces archaeologists to reassess their approaches and employ new methods to extract information from the remaining materials. The durability of stone as a building material is truly remarkable. It can last for millions of years if it is not subjected to unfavorable geological conditions. It is worth noting, however, that not all stones have the same resistance. For instance, limestone is susceptible to erosion and destruction by water and acid, leading to its rapid deterioration even compared to denser rocks like granite or basalt. Ancient civilizations such as the Egyptians used stone to construct grand pyramids that were meant to endure for centuries. However, over the course of millennia, many of these structures could completely disappear due to factors such as earthquakes, the uplift and subsidence of the Earth's crust, and human activity. For example, in Mesopotamia, where climatic conditions played a role, many stone buildings were destroyed due to constant flooding and the action of groundwater, which could cause them to settle. Furthermore, many stone temples and palaces were abandoned and, over time, their structures were destroyed by wind and rain. As a result, even massive stone structures can remain only as shadows of their former glory if they are not protected from natural disasters or human activity. In some regions with less favorable climates, such as deserts or tropical forests, stone buildings can last longer, but they are still subject to destruction. It is important to consider that even in the most ideal conditions, stone is not eternal, and many ancient monuments that once symbolized the power of civilizations now exist only as ruins. Metals, despite their apparent strength, cannot boast of durability in geological timescales. Even the highest quality alloys, such as stainless steel, are subject to corrosion and oxidation over time. This occurs due to the influence of moisture, oxygen, and other environmental factors. For instance, iron used in building construction and bridges can begin to rust within just a few decades, if not protected by special coatings. Bronze. In geological time, which spans millions of years, even the most resistant metals like gold or platinum are subject to changes. Although they do not corrode as quickly as other alloys, their surfaces can still be eroded. Consequently, many ancient metallic artifacts, such as swords or coins, lose their shape and structure, becoming barely noticeable traces on the Earth's surface. Therefore, metallic objects that were once the pride of civilizations can disappear, leaving only hints of their existence. Organic materials such as wood, textiles, and paper pose a significant challenge for archaeologists and historians. These materials decompose within a few years, or at best, centuries, leaving virtually no traces for future researchers. For instance, wood begins to rot within a few decades, especially in high humidity or temperature conditions. Natural fiber textiles also degrade rapidly. Cotton and linen can last for several decades, while wool may last a bit longer, but still not for millennia. Paper, which became widespread from the beginning of the second millennium, is susceptible to the effects of oxygen and light, leading to yellowing and deterioration. The conditions of burial play a crucial role. For example, in dry and cold environments, organic materials can last longer, as seen with Egyptian mummies, where the dry climate helped preserve textiles and skin. However, even when these materials are found, they are often in such a state that they cannot be identified or restored. Researchers must rely on indirect evidence and written sources to reconstruct the past, greatly complicating their work. As a result, organic materials become a major vulnerability in the study of history, and archaeologists often can only speculate about the appearance of everyday items from ancient civilizations. The concept of technological signature of a civilization reflects how various societies expressed their uniqueness through the use of technologies and materials in everyday life. Each culture leaves its mark on history, manifesting through the specifics of production, architecture, and art. The technological signature encompasses not only the tools and mechanisms used by people, but also the ways they adapted to their environment, utilized resources, and interacted with one another. This trace helps researchers understand how civilizations developed and what factors influenced their evolution. For instance, the specifics of material processing, the choice of construction technologies, and agricultural methods can reveal much about social structures, economic models, and even the worldview of a people. The technological signature serves as the key that opens the doors to the past and allows us to see how different nations dealt with the challenges of their time. It is important to note that this trace is not always evident. Sometimes it is hidden under layers of time, and archaeologists must demonstrate ingenuity to restore the picture. Many aspects of the technological signature may be lost or distorted, making it difficult to understand the true picture of civilization's development. For example, the use of a particular material may indicate a high level of technological complexity in one case and simple but effective solutions in another, found in response to specific societal needs. Different approaches to the same challenge can demonstrate not only the level of technological progress, but also cultural differences between peoples. These nuances make the study of the technological signature not only fascinating but also complex, requiring scholars to be attentive and engage in deep analysis. Today, the study of the technological signature of civilizations remains a relevant direction in archaeology and history, opening new horizons for understanding our past. The technological signature is typically traced in artifacts found by archaeologists and helps restore not only the functionality of objects, but also their cultural significance. For instance, the choice of certain forms and styles can indicate the influence of neighboring cultures or traditions passed down through generations. Radioactive isotopes serve as unique markers that can persist in geological layers for millions and even billions of years, providing evidence of human technological activity. For instance, carbon-14, which is formed in the atmosphere and subsequently absorbed by living organisms, allows archaeologists to date the remains of ancient civilizations, as its level in the atmosphere changes over time. Other isotopes, such as strontium-90, can indicate the use of specific technologies related to nuclear energy, leaving traces in geological layers. For example, after nuclear tests in the mid-20th century, the level of strontium-90 sharply increased, enabling scientists to track the history of these events through geological samples. Furthermore, highly active isotopes like plutonium-239 can testify to human activity on Earth even millions of years after their appearance. These isotopes, entering soil and rock formations, create a sort of time capsule that can be discovered during geological research, providing scientists with valuable data on how technologies have evolved and where key events have occurred. Analysis of such markers helps restore the picture of the past, including the consequences of nuclear energy and its impact on the environment, which is a crucial aspect for understanding the technological evolution of humanity. Studies conducted in various regions of the world show that radioactive isotopes can be found in different geological conditions, making them a universal tool for studying not only the history of technologies, but also the ecological consequences of their use. Synthetic materials and polymers are unique artifacts that can serve as long-term witnesses to technological civilization. These materials, created by humans, do not decompose as quickly as organic substances and can persist in geological layers for millions of years. For instance, plastic, invented at the beginning of the 20th century, is already forming its own layers in soil and on the ocean floor. Research shows that in some regions, such as the Arctic Ocean, floating islands of plastic waste are forming new ecosystems that will be studied by future geologists. Polymers like nylon and polyethylene are highly resistant to ultraviolet radiation and chemical substances, making them ideal candidates for preservation in the geological record. For example, in areas with particularly high levels of pollution, so-called plastic layers are formed, which can tell us about human activity in prehistory. These layers can serve as a basis for studying changes in ecosystems and climate related to industrialization and mass consumption. Additionally, synthetic materials can be found in archaeological excavations, helping scientists understand how lifestyle and technologies changed throughout different historical periods. In the 21st century, Due to globalization, plastic products are spreading, leaving traces in geological history, much like stone tools did in ancient times. Scientists are already detecting the presence of microplastics in samples from ancient deposits, opening new avenues for research. For instance, in Mesopotamia, archaeologists have found evidence that the Tigris and Euphrates rivers altered their courses due to human activities related to irrigation and agriculture. Research shows that the ancient Sumerians, using irrigation systems built over 5,000 years ago, significantly increased soil fertility, leading to population growth and urban development. In other parts of the world, such as South America, the Maya Indians also modified natural conditions by building complex terraces and canals for land cultivation. In the Caribbean basin, archaeologists have discovered that the Mayas' active agriculture led to soil erosion and changes in the hydrological regime, affecting local ecosystems. These changes were not always sustainable. Many civilizations, like the Incas, faced resource depletion issues, which also left traces in geological layers. In some cases, such as in the Nile region, research shows that ancient Egyptians altered the river's level using dams, affecting the distribution of rainfall and biodiversity. These examples demonstrate how human activity can reshape landscapes and ecosystems, leaving clear traces in the geological record. Scientific methods such as paleoecology and sediment analysis help scientists reconstruct these changes, revealing how civilizations adapted to their conditions and what consequences this had for the surrounding environment. Scientific skepticism is a crucial tool in evaluating unusual hypotheses and theories, as it enables a critical approach to information and verification of its reliability. Skepticism does not mean rejecting new ideas. Rather, it encourages researchers to ask questions and seek evidence before accepting anything at face value. In a world where many myths and misconceptions coexist with scientific discoveries, this approach helps to separate facts from fiction. For instance, when bold theories about ancient civilizations or their achievements emerge, scientific skepticism requires us to delve deeper into the sources of information, check their reliability, and compare them with other data. This approach helps to avoid errors and misunderstandings that may arise from insufficient knowledge or bias. It is important to understand that even the most intriguing hypotheses require rigorous testing, especially if they contradict established knowledge. For example, when discussing the existence of mythical creatures or floods based on legends, scientific skepticism helps us question the reality of these events and their interpretations in different cultures. This approach not only enriches our understanding of the past, but also protects us from misunderstandings, allowing us to maintain a balance between openness to new ideas and the necessity of their critical evaluation. Scientists working in various fields apply this principle to deepen their knowledge and perspectives on the world, leading to a more comprehensive study of historical processes and cultural changes. Ultimately, scientific skepticism becomes a key element in any investigation, helping us to maintain clear thinking and remember that every claim should be backed by evidence. The principle of Occam's razor is a crucial tool in the scientific approach, which asserts that among several potential explanations for a single phenomenon, the simplest one should be chosen. This principle was formulated in the 14th century by the English philosopher William of Ockham, who emphasized that one should not multiply entities without necessity. In other words, if two explanations can describe the same phenomenon, the one that requires fewer assumptions is preferable. For example, if we observe that plants grow better in one location than in another, two possible explanations could be: the first is the result of more fertile soil, and the second is the influence of magical rituals performed by local residents. Applying Occam's razor, we would likely choose the first explanation, as it does not require additional, unfounded assumptions about magic. In scientific research, this principle helps avoid overly complex theories, allowing researchers to focus on factual data and their logical interpretation. It serves as a reminder that simplicity often means greater probability, and complex constructions without supporting evidence can confuse the investigation and distract from the essence of the matter. In practice, this allows scientists to make more accurate conclusions and avoid pitfalls where excessive complexity leads to errors in analysis. Scientific works following this principle become more transparent and understandable, which in turn facilitates a better understanding of complex phenomena. Occam's razor remains relevant in modern research, where the need for clarity and simplicity in explanations becomes particularly important amidst the growing volume of available information. The need for extraordinary evidence for extraordinary claims becomes particularly evident in the context of hypotheses about ancient, prehistoric civilizations. For instance, claims of complex architecture or writing must be supported not only by artifact finds, but also by clear evidence of their dating and context. When archaeologists report findings such as mysterious stone structures or unusual tools, it is crucial that these artifacts are thoroughly investigated using modern methods, such as radiocarbon dating or isotope analysis. Without such verification, any claims about ancient civilizations remain mere speculations. Furthermore, historical documents, if they exist, must be authenticated and interpreted in the cultural context of their time. For example, reports of great civilizations that might have existed before the beginning of written history require archaeological finds that could either confirm or refute these ideas. This means that before accepting such theories, scientists must gather sufficient data to leave no room for doubt. Otherwise, they risk entering the realm of myths and fables. Scientific debates around such hypotheses demonstrate that even the most intriguing ideas need rigorous testing and substantiation. Therefore, when it comes to claims about ancient civilizations, extraordinary evidence is not just desirable, but necessary. Archaeologists continue to explore sites like the Nazca Plateau in Peru, where geoglyphs astound with their complexity and scale, but for recognizing their creators as a highly advanced culture, more substantial evidence is required. For instance, systematic analysis of artifacts and cultural layers using various disciplines such as archaeology, anthropology, and paleogenetics allows for precise dating of finds and understanding how people lived in specific regions. These methods enable the reconstruction of social structures, economic systems, and even climatic conditions in which ancient societies existed. It is important to note that the integration of data from different scientific fields, such as geography and ecology, helps to recreate a complete picture of life in the past and to identify connections between various cultures. Furthermore, the use of mathematical models and statistical methods allows researchers to formulate hypotheses about the migration of peoples and their interactions, significantly expanding our understanding of historical processes. Scientific research is becoming increasingly multifaceted, taking into account not only material finds but also cultural contexts, which allows for a deeper understanding of how ancient civilizations influenced each other and their environment. Thus, contemporary approaches provide scientists with powerful tools for analyzing and interpreting data, enabling the discovery of new connections and a deeper understanding of how human history was shaped. In this context, the discovery of more precise traces of ancient cultures becomes possible and opens up new prospects for further research. Research shows that the interaction of various scientific disciplines plays a key role in unraveling the mysteries of our past. For instance, using LiDAR, which emits laser beams and analyzes their reflections, archaeologists have been able to uncover previously invisible ruins of ancient cities in places like Central America. LiDAR enables the penetration of forest areas and the identification of geometric shapes that indicate the presence of buildings and roads hidden under vegetation. In a recent study in Guatemala, over 30,000 new structures, including pyramids and aqueduct systems, were discovered, significantly altering our understanding of the scale of the Maya civilization. Satellite mapping, on the other hand, allows for the examination of large territories by collecting data on topography and landscape changes that may indicate human activity. For example, The use of satellite imagery in Egypt led to the discovery of ancient canals and agricultural fields that were previously thought to be lost. These technologies not only enhance the efficiency of archaeological excavations, but also reduce the need for physical intervention in the ground, which is particularly important in protected areas and hard-to-reach regions. Therefore, satellite mapping and LiDAR have become indispensable tools for archaeologists, enabling not only the discovery of new objects, but also the re-evaluation of existing theories about the development of ancient civilizations. In particular, these technologies have shown that many well-known historical sites have a more complex structure than previously thought, requiring new approaches to the interpretation of historical data. Methods of mass spectrometry and isotopic analysis play a crucial role in determining the age and origin of historical materials. Mass spectrometry allows for the analysis of sample composition, breaking them down into constituent parts and determining the relative content of various isotopes. For instance, using this method, scientists can establish the age of wood by analyzing the ratio of carbon isotopes, which can indicate when the tree was felled. Isotopic analysis, in turn, can reveal unusual isotope ratios that may suggest technological processing of materials or their origin from specific geographical zones. For example, studying the isotopes of oxygen in ceramic samples can indicate where they were produced, as different regions have characteristic isotopic signatures. These methods open new horizons in archaeology, enabling researchers to not only accurately date artifacts, but also understand the technological processes used in their production. In particular, for example, the analysis of ceramic with high concentrations of certain isotopes may suggest high temperatures used in firing, indicating the advanced technologies employed in antiquity. Computer modeling and simulations play a crucial role in the reconstruction of ancient ecosystems and climatic conditions. For instance, these technologies can simulate temperature changes, precipitation levels, and even ocean currents over thousands of years. This helps researchers determine which climatic conditions were favorable for the development of complex life forms and civilizations. A notable example is a study conducted in the early 2000s where models were created to show how climate changes during the Pleistocene facilitated the migration of ancient humans. These models consider not only temperature changes but also the interaction of various species, allowing us to understand how ecosystems responded to climatic fluctuations. For example, analyzing ancient rivers and their flows using models helped identify how civilizations like the Sumerians could adapt to changes in water availability. Thanks to these studies, scientists can more accurately assess the factors that contributed to the prosperity or decline of civilizations such as the Maya or the Incas in changing climatic conditions. It is worth noting that such technologies not only aid in understanding the past, but also serve as tools for predicting future ecological changes, making them indispensable in contemporary scientific research. Consequently, the application of computer modeling enables the creation of a more comprehensive understanding of the interaction between humans and nature over centuries. The concept of the Anthropocene emphasizes how human activity has transformed the planet at all levels, from climate and ecosystems to geological processes. This has been facilitated by phenomena such as industrialization, urbanization, and globalization, which have presented new challenges to the environment. For instance, anthropogenic carbon emissions have led to global warming, while large-scale deforestation has altered the landscape of entire regions and threatens many species on the brink of extinction. This also raises questions about sustainable development, as resources are being depleted faster than they can be replenished. At the same time, changes in land use, such as agriculture, have created new ecosystems, but also led to soil degradation and loss of biodiversity. Humanity now faces the need to rethink its relationship with nature and reassess approaches to its conservation and restoration. This new era requires us to recognize our responsibility for the planet and actively participate in its preservation. In this context, it is worth noting that human influence on geological processes is even evident in changes in tectonic plate movements and the formation of new landforms. Plastic layers in sedimentary deposits serve as a unique geological marker that will testify to the existence of human civilization over millions of years. Since the scientists have already found microplastics in samples from the ocean floor and in Antarctic ice, confirming its widespread distribution. This layer will serve as an indicator not only of the presence of plastic, but also of the entire era when humanity actively used synthetic materials. As a result, the plastic we use today will serve as a kind of memorial for future generations, leaving an indelible mark on the geological history of Earth. Research shows that a layer with plastic deposits can be found at depths of several meters, giving an idea of the scale of its distribution. In the future, scientists will be able to extract information about our time by analyzing air bubbles preserved in ice cores. These cores, for example, have been retrieved from the Greenland and Antarctic ice sheets, and they show how the levels of carbon dioxide and methane have changed over thousands of years. This increase is directly linked to the Industrial Revolution and the widespread burning of fossil fuels. Furthermore, the analysis of ice cores can also reveal changes in the levels of ozone and other greenhouse gases that affect the Earth's climate system. Thus, research shows that changes in the atmosphere's composition can serve as a significant indicator of anthropogenic impact on the climate, as significant increases in carbon emissions are observed in specific historical periods, such as the early 20th century. Meanwhile, it can be expected that future geologists will find traces of new synthetic substances, such as freons and other chemical compounds used in production and daily life, in these samples. These data will help create a comprehensive picture of how a technological civilization has influenced planetary processes. Massive scientists are already documenting a sharp decline in the populations of many animal and plant species, which will undoubtedly leave clear traces in the geological layer for future researchers. For instance, according to the International Union for Conservation of Nature, in the 21st century, around 1 million species are at risk of extinction, the highest rate ever recorded. This extinction is driven by numerous factors, including habitat destruction, climate change, and environmental pollution. For example, deforestation in the tropics leads to the loss of unique ecosystems like the Amazon rainforests, which are home to many species found nowhere else. In the geological future, when the remains of these extinct organisms are studied, scientists will be able to determine what caused this sudden decline in biodiversity. By comparing layers of sedimentary rocks, they will see how human activity, starting with the Industrial Revolution, has had a powerful impact on the biota of the planet. These data will be a crucial part of the study of the Anthropocene, the epoch in which human activity becomes the dominant force shaping the Earth. As a result, future geologists and biologists will see clear signs of mass extinction, which they will be able to link to specific human actions such as pollution, hunting, and climate change. Civilizations, like living organisms, go through their own life cycles: birth, flourishing, decline, and ultimately disappearance. This process can be seen as a philosophical question. Does history repeat itself, or does each epoch bring something new and unique? Do the same mistakes recur, or does humanity, despite its flaws, find new paths and solutions? Throughout different historical periods, we observe civilizations reaching the peak of their power, only to then face internal and external crises that can lead to their downfall. Is this an inevitable part of human nature, or the result of specific events and decisions? These questions prompt important reflections on how society responds to the challenges of time and what lessons it can draw from its past. For instance, some societies learn to adapt and evolve in response to changes, while others prove less flexible, leading to their decline. The contrast in approaches and reactions to crises can be a key factor in understanding the dynamics of civilizations. This topic also encourages us to consider how contemporary society deals with challenges such as global warming or social inequality, and what strategies can be effective in preventing decline. The importance of analyzing these cycles cannot be underestimated, as they can provide insight not only into our history, but also into our future. In this context, it is worth noting that many researchers point to parallels between different civilizations in their pursuit of power and influence, which ultimately leads to conflicts and wars. These aspects emphasize that in the context of globalization and the interconnectedness of the world, lessons from the past may be more relevant than ever. For example, many historians assert that lessons learned from the fall of the Roman Empire can be applied to modern states facing economic and social difficulties. It is important to remember that each civilization leaves its mark on history, and this mark can be both positive and negative. In some cases, as with the ancient Egyptians, achievements in science and art continue to inspire humanity even after thousands of years. These examples underscore that while the cycles of civilizations may be inevitable, each one also presents unique opportunities for growth and development. There are numerous factors contributing to this cycle, from climate to political decisions, from cultural changes to economic crises. Ultimately, whatever factors influence civilizations, they are always subject to change and evolution, making their study particularly important for understanding our place in the world. The concept of the Great Filter in Fermi's theory posits a hypothetical barrier that hinders the development and long-term survival of technological civilizations in our universe. This idea raises the question, if there are many potentially habitable planets in the universe, why do we not see clear signs of extraterrestrial life? The Great Filter suggests that there are certain stages or events on the path to advanced civilizations that are either difficult to overcome or that destroy nascent civilizations. This could be due to various factors such as catastrophic natural events, wars, technological disasters, or even self-destruction. Some scientists believe that the filter lies in the past, implying that many species did not overcome these critical stages, such as the development of complex life or the transition to a technological society. Others, for example, global warming, nuclear wars, or pandemics could be the very filters that destroy humanity on its way to the stars. This theory implies that if we cannot overcome these barriers, our fate will be similar to that of many other civilizations that disappeared at various stages of their development. This concept sparks many debates and controversies among scientists and philosophers, raising numerous questions about our future and how we can adapt to the challenges that the universe presents to us. It is important to note that the Great Filter does not have a single explanation and remains an active area of research and discussion. Self-destruction as a possible fate of technological civilizations is a subject of much debate among scientists and futurologists. One hypothesis suggests that civilizations reaching a certain level of development encounter internal contradictions that lead to their collapse. Factors such as nuclear wars, ecological disasters, and social conflicts can act as catalysts for self-destruction. Some researchers, like astronomer Martin Rees, argue that advanced technologies could ultimately lead to the destruction of the civilization that created them. This could explain why we do not find clear traces of ancient intelligent beings on Earth. Perhaps they reached a level of development that became their fatal mistake. Historical examples, such as the Mayans and Incas, experienced sudden declines, possibly due to excessive resource exploitation and climate changes. If similar scenarios occurred on other planets, it might explain why we do not see their traces in our cosmos. The development of technologies without adequate control and understanding can lead to catastrophe, which could explain why we do not receive signals from other intelligent civilizations. Currently, the only traces of their existence may be mysterious artifacts that leave us with questions but not answers. Ruins of great structures like pyramids or megaliths could be evidence that other civilizations reached high levels of technology but ultimately could not overcome the challenges they themselves created. The essence of sustainable development lies in the balance between economic growth and the preservation of nature, enabling civilization to exist for millions of years without catastrophic consequences. For instance, one such example is the terraced farming systems used by the Incas in Peru. They created terraces on mountain slopes, which allowed for effective management of water resources and prevented soil erosion. Sustainable development also involves the use of renewable energy sources such as solar or wind power, which reduce dependence on fossil fuels and decrease the carbon footprint. It is important to note that sustainable development does not mean abandoning technology. Rather, its implementation requires innovative solutions that can provide financial benefits while also protecting the environment. Programs for ecosystem restoration, such as reforestation or water body cleanup, are also part of this concept and demonstrate that intelligent species are capable not only of destruction, but also of restoration. The question is whether modern societies can change their habits and management systems to ensure long-term harmony with nature, or will they once again face the same problems as their predecessors, risking catastrophe? For example, Germany's programs for transitioning to green energy have significantly reduced carbon dioxide emissions, providing a clear example of how to transform the economy towards sustainable development. The essence of this discipline lies in studying not only physical objects like satellites or space stations, but also cultural, technological, and historical aspects related to space exploration. This can involve analyzing artifacts left on the Moon or studying data from automated interplanetary stations that can reveal how humans perceive and interact with space. Space archaeology opens new horizons for understanding human history, allowing us to consider space missions as significant cultural events that shape our understanding of humanity's place in the universe. Unlike traditional archaeology, here the material aspect is not the only focus, but also the cultural values we attribute to these objects. For example, each launched satellite or every step on the surface of another planet can be seen as part of a broader narrative about humanity's desire to explore the unknown. This expands the boundaries of archaeology, allowing us to ask questions about how technologies and ideas move through time and space, and how they influence our understanding of history itself. This discipline not only actively develops scientific methods, but also creates new approaches to interpreting already known data, which in turn encourages scientists to re-evaluate traditional notions of what can be considered an archaeological object. The uniqueness of space archaeology lies in its ability to combine science, history, and philosophy, creating a multi-layered approach to studying our place in the cosmos. A key aspect is that, unlike terrestrial archaeology, which is limited by physical boundaries, space archaeology expands our understanding, allowing us to consider how human ideas about time and space evolve at a level that was previously considered unattainable. The Luna, for instance, features like craters can maintain their outlines for billions of years, whereas on our planet such formations are constantly changing. There are theories that some anomalies on the lunar surface, such as regular shapes and symmetrical structures, could be the result of artificial intervention rather than natural processes. Objects like lunar pyramids or lunar cities are discussed as potential evidence of extraterrestrial civilizations. Research using high-resolution satellite imagery suggests that some of these structures may not be mere optical illusions, but real formations requiring in-depth study. Furthermore, the absence of an atmosphere on the Moon means that any artificial objects built there could retain their form and structure for millions of years, unlike on Earth where rain, wind, and other natural factors erode human-made traces. This makes the Moon a unique object for searching for signs of ancient civilizations, as its surface could serve as a kind of time capsule, preserving information about life that may have existed in our solar system. Investigating the lunar surface with rovers and orbital spacecraft could lead to new discoveries that will change our understanding of humanity's place in the universe. Currently, experiments using highly sensitive instruments such as radars and spectroscopes have already identified some anomalies that require further analysis. Research into Mars in search of signs of life has become one of the most ambitious tasks in astronomy and planetary science. The red planet once had conditions similar to Earth, including the presence of liquid water on the surface and a denser atmosphere. Scientific missions such as Mars, rover Curiosity and Perseverance are actively studying the geological and atmospheric conditions, analyzing soil and rocks for organic compounds. One of the key discoveries has been the presence of clay minerals in craters, indicating prolonged interaction between water and rock. Researchers have also found methane in Mars's atmosphere, which could suggest a biological origin for the gas, although non-biological sources like geothermal processes also exist. It is important to note that in the past, Mars had extensive oceans that could have supported life. Special missions are focused on studying subsurface ice, which may preserve traces of ancient microorganisms. Additionally, in the Jezero crater, where Perseverance is currently operating, scientists are investigating sedimentary rocks that could contain artifacts left by possible Martian life forms. These studies will help us understand how complex organisms could have existed on the planet billions of years ago. The scientific community is actively discussing the possibility of the existence of Martian microorganisms that could have been the ancestors of life on Earth. One hypothesis suggests that meteorites that fell to Earth could have brought Martian bacteria, opening new avenues for studying life in the universe. At present, data from Martian missions continue to inspire scientists to conduct further research, with the goal not only of finding life, but also understanding the evolution of planetary systems. Scientists hypothesize that such objects could serve as cosmic janitors, leaving behind evidence of their visits or utilizing resources from these celestial bodies. For instance, asteroid Bennu, which was explored by the OSIRIS-REx mission, has a unique structure, and its composition may provide insights into the potential for resource processing. Similarly, such research also considers comets, which may contain not only organic compounds but also water, essential for biological processes. Studies show that comets like Churyumov-Gerasimenko may harbor complex molecules, indicating the possibility of past life forms or technological activity. Scientists are also beginning to consider the development of tools for on-site analysis of such objects, which would provide more accurate data on their composition and structure. Certainly, it is important to note that the search for altered asteroids is part of a broader program to explore the solar system, where each new object can contribute significant information about the past and future of humanity. One example of such an object is asteroid Humboldt, which has an unusual orbit and structure, also attracting the attention of researchers. Planetary engineering as a concept aims to alter or adapt planetary conditions to improve their suitability for life. For instance, it is proposed that various scientific approaches could transform Mars' atmosphere to make it more Earth-like, opening new horizons for colonization and exploration. In this field, researchers are actively exploring the potential use of microorganisms and other organisms to change the chemical composition of the atmosphere, as well as the application of various energy sources for heating planets or creating protective magnetic fields. Additionally, planetary engineering may include ideas for creating artificial ecosystems that could support life in conditions unsuitable for humans. Such concepts generate both interest and criticism in scientific circles, as they raise numerous ethical and ecological questions related to interfering with natural processes. Astronomers and astrophysicists continue to investigate how far we can go in altering planetary ecosystems and what the consequences of such manipulations might be. One aspect that particularly interests researchers is the study of potential risks associated with global climate change on other planets and the impact on existing ecosystems. Scientific research in this area continues, and while there are no final answers yet to questions about the success of planetary engineering in the near future, Each new discovery brings us closer to understanding how we can adapt other worlds to meet human needs and what resources will be required. Scientists continue to discuss this topic, and its relevance is growing in the face of increasing resource problems on Earth. Terraforming is a process of deliberate climate and ecosystem modification on a planet to create conditions suitable for life. For instance, terraforming may involve introducing specific microorganisms that produce oxygen or fix carbon dioxide, helping to create more favorable living conditions. It could, for example, if water resources on Mars were actively used to create oceans, this would lead to the formation of new geological formations and changes in the planet's topography. On Earth, we already observe similar processes. The construction of dams and reservoirs alters river courses and drainage systems, leaving traces in the geological record. Therefore, terraforming not only creates conditions for life, but also changes the planet's nature at a geological level. Scientific research indicates that such changes can be irreversible, and their consequences may be felt for millions of years. One of the most fascinating aspects of potential traces of highly advanced civilizations is the existence of megastructures that could remain on Earth and in space even after their disappearance. For instance, artificial satellites orbiting our planet could serve not only as communication and navigation tools, but also as evidence of technological progress. Their orbits, durable and stable, could preserve information about past civilizations for centuries, even if the structures themselves eventually crumble. More ambitious projects, such as space elevators designed to facilitate access to orbit, could leave behind massive plans visible even from Earth. If such orbital rings similar to those found around planets in our solar system could be created for aesthetic or practical purposes, leaving behind vast debris scattered in space. In the event of such a civilization's disappearance, these megastructures would become silent witnesses to its existence, leaving behind questions about how and why they were created. Moreover, these structures could influence the surrounding environment, affecting both physical and biological processes on the planet. For example, satellites could affect Earth's magnetic fields. In the past, they could have served not only for observation, but also for manipulating climate conditions, raising even more questions about their long-term effects. Studying such megastructures could provide insight not only into the technological level, but also into the social, economic, and cultural aspects of life in a highly advanced civilization. Ultimately, these artifacts could become an important part of our understanding of the history of the universe and the civilizations that once inhabited it. In our present time, we can only speculate about the specific megastructures that might remain from extinct civilizations, but their existence opens new horizons for research and contemplation about our place in the cosmos. Fractal architecture is a concept where the shapes and structures of buildings mimic the geometric patterns found in nature. This means that buildings can appear as an extension of their surroundings rather than as separate artificial objects. For instance, such constructions can have varying levels of detail, where smaller elements repeat larger forms, much like the leaves of a tree mirror the shape of the entire tree. Biomorphic constructions, in turn, draw inspiration from biological systems, allowing for the creation of buildings that harmonize with nature. For example, buildings mimicking the forms of coral reefs can appear as part of the ocean floor, while structures inspired by plant forms can seem like natural extensions of the flora. Modern technologies such as 3D printing enable the creation of complex fractal structures that would be impossible with traditional construction methods. These innovations open up possibilities for urban planning and sustainable development, where architecture not only exists but also actively interacts with the ecosystem, raising questions about how we perceive the boundaries between the natural and the artificial. In such conditions, artificial objects can become indistinguishable from natural forms, presenting unique challenges for future archaeological research and the preservation of cultural heritage. Interestingly, such approaches are already being applied in some contemporary projects, such as the Smart Castle in China, which was designed with principles of biomimicry, combining advanced technologies with nature. Cultural blindness manifests in the perception of customs, norms, and values that do not align with what is familiar to an individual. For instance, many people may not realize that their own views and behavior are shaped by cultural context, leading to the dismissal or misunderstanding of alternative perspectives. This phenomenon can have serious consequences, especially in a globalized world where interaction between different cultures is becoming increasingly frequent. Those suffering from cultural blindness may miss out on crucial aspects of communication and relationships, making it difficult to build trustful connections. The problem is exacerbated when cultural differences are seen as barriers rather than opportunities for exchange of experiences and knowledge. For example, in business, a lack of understanding of cultural norms can lead to unsuccessful negotiations or even conflicts when one party does not understand the behavior of the other. It is important to recognize that cultural blindness can hinder not only personal relationships, but also professional interactions, underscoring the need for education in intercultural communication. Moreover, in the face of global changes such as migration and international connections, awareness of cultural differences becomes crucial for successful integration and cooperation. As a result, understanding and acknowledging cultural differences becomes a key task for modern societies striving for harmony and mutual understanding. In this context, studying cultural blindness helps to identify mechanisms that promote deeper understanding and respect between different groups. For instance, this results in many researchers rejecting ideas of highly advanced societies that existed before the emergence of known civilizations, such as Mesopotamia or ancient Egypt. Moreover, scientists daring to propose unconventional ideas often face ridicule and criticism from their peers, further discouraging independent research. Additionally, there is the availability bias, where researchers place greater value on data that is easily accessible, such as artifacts from known civilizations, while less well-known findings, potentially indicating technological achievements of ancient societies, remain overlooked. Nevertheless, despite these barriers, some archaeologists and historians still attempt to study enigmatic artifacts, such as mysterious stone structures, which could indicate the existence of complex technologies in antiquity. For example, discoveries at Göbekli Tepe in Turkey, dating back to the 10th millennium BCE, demonstrate that people could possess substantial architectural knowledge even before the advent of writing. These findings challenge the traditional view of human civilization's progress and open new avenues for research. Anthropocentric bias in science manifests in numerous aspects from history to biology and forms the basis for how we perceive the evolution of intelligence. Often, this leads to the neglect of alternative forms of intelligence, such as animal behavior or even systems created by humans, like artificial intelligence. For instance, certain species of dolphins and birds exhibit complex communication and problem-solving abilities. Research shows that these animals have their own ways of transmitting knowledge, which can be comparable to human methods, but do not require language in the conventional sense. Moreover, the notion that only humans are capable of abstract thought is also called into question. Furthermore, in this context, it is important to consider how we define intelligence and reason, as these categories may be much broader than commonly believed. Complex systems such as ecosystems or even the internet can exhibit their own form of intelligent behavior, although not comparable to human intelligence. It is possible that if we stop placing ourselves at the center of the universe, we could open new horizons in understanding how different forms of intelligence can interact and develop. Scientific research that ignores these alternative paths risks missing out on important lessons about how the world around us functions. Ultimately, anthropocentrism not only limits our understanding of the past, but can also seriously hinder our vision of the future. Scientific discoveries in zoology and ecology show that many animals have their own ways of processing information and making decisions, which can be just as complex as those of humans. The problem of recognizing technologies that are radically different from our own is becoming increasingly relevant in the context of historical and archaeological research. We often assume that past civilizations used materials and sources of energy similar to those available to us today. However, this may be far from the truth. For instance, imagine that ancient societies could have used biomass or even geothermal energy sources for their needs, while we are accustomed to fossil fuels and electricity. Traces of such technologies may not be immediately apparent to a modern person. This, for example, if a civilization used organic materials such as wood or plant fibers in construction, their buildings might not have survived in conditions where climate changes or natural disasters would have destroyed them. Additionally, the lack of metallic artifacts or other traditionally recognized signs of progress can lead to an underestimation of the level of development of such cultures. For instance, some researchers suggest that in South America there existed societies that used complex irrigation and agricultural systems, but their traces are difficult to find due to the landscape's vagueness and subsequent changes in the ecosystem. It is also important to remember that in some regions, ancient civilizations could have used local varieties and minerals that are unfamiliar or inaccessible to modern scientists today. This further complicates the task of accurately reconstructing the way of life and technologies of those who lived thousands of years ago. In such cases, we risk missing out on important lessons and examples of human ingenuity and adaptability that do not fit into our contemporary notions of technological development. This is precisely the case where different cultures facing the same conditions choose their unique paths to solving the same problems. For instance, while some societies develop certain technologies, others may focus on different aspects, creating their own innovations that might be more effective for their specific environment. Such paths often go unnoticed in historical research, as the emphasis is placed on more well-known and widespread achievements, while less popular options fall out of sight. This leads us to overlook the rich diversity of human experience and ingenuity that could enrich our understanding of how technologies can adapt and evolve. Examining these alternative paths can help us better understand how different cultures have dealt with the same challenges and what lessons can be learned from their approaches. In some cases, this may mean that even without access to certain resources, societies found ways to survive and thrive that might seem unusual to us, but were nonetheless effective. Thus, this can be seen in various aspects such as agriculture, construction, or the organization of social life. Each of these aspects deserves careful study to evaluate how they shape the development of different communities and how they might be applicable today. It is important to understand that such parallel paths are not just alternatives, but full-fledged models that could offer us new perspectives on familiar problems. Technologies do not exist in a vacuum, and their development is always influenced by cultural, social, and economic factors that must be taken into account. Biotechnological development represents an alternative approach to mechanical progress, focusing not on the creation of machines, but on the modification of living organisms. This approach could enable humanity to create organisms adapted to their environment, capable of performing tasks traditionally assigned to machines. For instance, imagine a world where, instead of gasoline-powered tractors, people used genetically modified plants or microorganisms to efficiently till the soil and produce necessary resources. Such organisms, unlike machines, would not leave traditional archaeological traces. Their impact would be more evident in ecosystems and genetic changes to the environment. Consider the experiments with genetically modified bacteria used for oil spill cleanup, demonstrating how living organisms can solve complex problems. Developing such technologies would require a deep understanding of biology and ecology, but would also lead to new achievements in agriculture, healthcare, and environmental management. For example, such organisms could be used to produce pharmaceuticals or combat pests, reducing the use of chemicals. However, despite the advantages, these technologies also raise ethical and ecological concerns related to interfering with nature and the consequences for biodiversity. Research in synthetic biology already allows for the creation of new organisms with specific properties, opening up new horizons for the future. For example, in 2022, scientists created a bacterium capable of breaking down plastic, illustrating how biotechnologies can transform our approach to contemporary issues. Such a path of development implies not only technological changes, but also a re-evaluation of our role in ecosystems, which could lead to radical shifts in our perception of nature and our interaction with it. Quantum technologies represent one of the most fascinating paths of development that could shed light on the possibilities of ancient civilizations. These technologies are based on the principles of quantum mechanics, where particles exhibit strange behavior. They can exist in multiple states simultaneously, and interactions between them can occur instantaneously, regardless of distance. This opens up prospects that could be used to manipulate fundamental forces of nature, such as gravity and electromagnetism, which could lead to the creation of technologies that leave no material traces. For example, imagine a civilization capable of using quantum fluctuations to create anti-gravity devices. Given that in ancient times technologies were often shrouded in myths and legends, it is possible that such achievements could have been misinterpreted as magic. In this context, it becomes interesting to investigate how quantum technologies could explain phenomena such as the flight of objects without apparent mechanisms or the creation of illusions that could astonish the imagination. For instance, the possibility of manipulating time and space within the framework of quantum physics opens new horizons for understanding how ancient people could have interacted with their surroundings. Such an approach would not only change our perception of history, but also raise questions about how far a civilization using quantum principles to solve everyday tasks could have advanced. There are even theories that such technologies could have been recorded in religious or cultural rituals that were passed down through generations, preserving knowledge of energy manipulation without leaving material artifacts. This also raises the question of how contemporary research in quantum physics could be connected to ancient knowledge that may exist in forgotten texts or oral traditions. Parallels between modern discoveries and ancient myths are becoming increasingly apparent, and each new discovery in the field of quantum technologies brings us closer to understanding what our ancestors truly knew and were capable of. Discoveries in quantum physics, such as quantum entanglement and superposition, can serve as a foundation for understanding not only technological achievements, but also philosophical questions about reality and our place in it. For instance, such beings could employ complex information transmission systems based on sounds, light signals, or even telepathy, enabling them to exchange knowledge and emotions instantaneously and without intermediaries. This could lead to the creation of virtual worlds where only concepts and ideas exist, rather than physical objects. Such worlds could operate through collective consciousness, where each participant contributes to the shared knowledge, creating a new In such systems, languages and symbols could evolve to levels beyond our comprehension, allowing the transmission of complex ideas without the need to materialize them in text or graphics. Imagine a community where information is transformed into emotions and sensations rather than being recorded on paper or in digital format, making communication deeper and more intuitive. Furthermore, such beings could develop methods of consciousness control, allowing each individual to alter their perception of reality, leading to the creation of new forms of art and self-expression that exist solely in the mental realm. In this part of their existence, such an approach fundamentally changes our understanding of civilization development, where material achievements such as buildings or machines lose their significance, and the primary focus becomes the advancement of knowledge and awareness. Without a doubt, such technologies open up infinite possibilities for the evolution of reason, but they also raise questions about free will and ethics, as the ability to manipulate consciousness can be used for both good and ill. In such circumstances, reason could become not just an instrument, but an active participant in shaping its environment, altering not only perception, but the very nature of existence. However, such theories remain in the realm of speculation until we encounter beings that can demonstrate the extent to which immaterial technologies can evolve. The concept of planetary consciousness encompasses the idea that humanity can evolve as a unified whole, coming together in a shared system of perception and understanding. In this context, interaction between people becomes more significant than individual achievements. One can imagine it as a colossal brain, where every thought and action forms a vast neural network. A crucial aspect is that this consciousness is not static. It is dynamic and subject to change, enabling humanity to adapt to new challenges and conditions. For instance, in such circumstances, every contribution, even the smallest, can have immense value, creating a multiplier effect. It is interesting to note that as technology advances and the amount of analyzable information increases, planetary consciousness becomes increasingly relevant. We see how social networks and various platforms connect people in ways that go beyond mere communication. They create shared spaces for the exchange of ideas and opinions. However, there is also a flip side. Such a network can be susceptible to misinformation and manipulation. Therefore, questions about how to manage this network and maintain its health become increasingly important in today's world. The future of planetary consciousness depends on how we use these tools to build a more sustainable and harmonious society. In this context, it is worth considering how various cultural and scientific approaches can influence the formation of this consciousness, creating a diversity of perspectives and approaches to solving common problems. The Gaia hypothesis, proposed by British scientist James Lovelock in the 1970s, posits that Earth functions as a single, self-regulating organism. Lovelock observed that the biosphere and geosphere interact with each other, maintaining conditions necessary for life. For instance, the level of oxygen in the atmosphere, ocean temperatures, and soil composition are kept in a constant balance by the activities of living organisms. This hypothesis challenges traditional views that ecosystems develop independently of one another. In the Gaia concept, nature is not merely a backdrop for human activity, but a complex network of interconnections where all elements work for the common good. Lovelock also suggested that Earth can be seen as a kind of organism capable of adapting to changes, thereby maintaining conditions necessary for the existence of life. This leads to an intriguing idea about planetary forms of intelligence. If Earth is indeed a self-regulating organism, it may possess its own form of intelligence, albeit different from human intelligence. Some scientists discuss the possibility that such forms of intelligence might be non-conscious, but still capable of managing ecosystems. For example, coral reefs, acting as a whole, can alter their composition and structure in response to changes in their environment. This idea has sparked debates among scientists and philosophers about how much we can anthropomorphize nature and attribute human-like properties to it. Nevertheless, the Gaia hypothesis raises important questions about how we perceive our place in the world and how our behavior impacts the planet as a whole. Lovelock argues that understanding Earth as a living organism can change our views on environmental conservation and sustainable development, emphasizing the need to care for the planet as if it were our own body. In this context, an important aspect emerges. The interaction between living beings and their habitat can be much more complex than we usually think. Specifically, Lovelock draws on examples where changes in one element of the system can trigger a chain reaction affecting other aspects of the ecosystem. For instance, deforestation can lead to climate change, which in turn affects all living things. The Gaia hypothesis, therefore, not only offers a scientific theory, but also raises ethical questions about our interaction with nature and the impact we leave on the planet. This network functions similarly to a brain, where each microbial cell plays a unique role but also contributes to the collective thinking of the community. For instance, microbes in the human gut not only aid in digestion, but also influence the host's mood and behavior by releasing neurotransmitters. This approach allows us to consider not only the individual existence of each microorganism, but also their interactions within a broader ecosystem, enabling the emergence of complex behaviors that cannot be explained by the actions of individual organisms alone. For example, when faced with pathogens, microbes can activate protective mechanisms, not only for themselves but for the entire community, highlighting their collective interests. Therefore, it can be hypothesized that microbiological collective intelligence is capable of adaptation and learning, responding to changes in the environment, and ensuring the survival of both individual organisms and entire ecosystems. This level of organization raises numerous questions about how microorganisms can form their decisions and how this interaction affects larger biological systems. Currently, scientists are still investigating the mechanisms underlying these processes to understand how this mind is formed from countless interactions and how it influences life as a whole. These underground structures, composed of thin threads called mycelium, can extend for kilometers and connect millions of trees and other plants. Research shows that mycelium can transmit not only nutrients, but also information between plants, allowing them to exchange signals about stresses such as drought or insect attacks. For instance, the mycelium of the Armillaria genus can form colonies spanning up to 30 square kilometers, enabling it to effectively interact with its surroundings. Moreover, it is important to note that mycelial networks not only contribute to the survival of trees, but also play a significant role in maintaining biodiversity by creating conditions for the growth of other species. For example, this opens new horizons for understanding ecosystems and their interactions, revealing how life on Earth is interconnected at a level previously unconsidered. Mycelial networks of fungi also attract the attention of scientists studying the potential use of these natural mechanisms in the modern world, as they offer potential solutions for creating sustainable communication systems and even for developing new technologies. Temporal chauvinism is a concept that implies a biased attitude towards the past or future based on temporal affiliation. For instance, some may consider only contemporary technologies and ideas to be truly important, while achievements of the past seem outdated or insignificant to them. Temporal chauvinism can manifest in various forms, from a condescending attitude towards cultural traditions to the criticism of historical figures based on modern moral and ethical standards. This phenomenon can hinder an objective assessment of the contributions of previous generations to the development of civilization, as it creates a distorted picture of historical progress that does not account for the complexity and diversity of human experience. Many researchers emphasize that such an approach can lead to a loss of understanding of the historical contexts in which significant events occurred. For example, the evaluation of certain actions or decisions made in the past may be too harsh if the circumstances in which these decisions were made are not taken into account. As a result, there is a risk of a simplistic view of history, which can lead to a misunderstanding of current socio-cultural processes and their roots. Notably, temporal chauvinism can be both conscious and unconscious, making it particularly dangerous because many may not be aware of the influence of their biases. This phenomenon also affects how we perceive cultural heritage, shaping our views on the value of certain artifacts or traditions. Ultimately, temporal chauvinism underscores the need for a critical approach to historical facts and their interpretation, which helps avoid the trap of one-sided perception. This is important for a deeper understanding not only of historical events themselves, but also of their impact on contemporary society. In such conditions, we can see that the perception of history and culture requires a comprehensive and balanced approach that takes into account various perspectives. For example, instead of ignoring or condemning the achievements of past eras, it is better to consider how they have influenced our present. For instance, there is a widespread belief that ancient civilizations such as the Sumerians or Egyptians were far from the current level of development. However, this view overlooks facts that indicate a high level of technology and culture in those times. For example, the Sumerians not only invented the wheel, but also developed the first writing system, cuneiform, which testifies to advanced forms of communication and administration. Similarly, the Maya civilization developed calendars that were more accurate than European ones for many centuries, taking into account astronomical phenomena such as solar and lunar eclipses. This bias in the perception of history as a linear progression, where each new generation supposedly surpasses the previous one, does not account for the fact that the development of civilizations can take various forms. Many artifacts found in different regions of the world indicate that highly developed societies existed long before our time, but their achievements often remain in the shadows of modern stereotypes about the primitivity of antiquity. For example, in Mesopotamia, complex systems of taxation and trade were recorded, which allowed society to function at a high level. Comparing technologies and social structures in different historical periods requires a deep analysis, not superficial judgments. It is important not to forget that many ancient civilizations possessed knowledge and skills in areas such as medicine, astronomy, and mathematics that often outpaced their time. In this context, it is crucial to consider that our modern notions of progress are often distorted by our contemporary views and biases. There are numerous examples that ancient peoples could achieve high levels of organization and technology that we sometimes underestimate or even ignore, which can lead to a distortion of historical truth. For example, archaeological finds in Peru show that the Incas built complex roads and bridges that connected remote regions, allowing them to maintain the unity of their empire. The history of humanity is replete with examples of cyclicality, where technological societies emerge, reach their zenith, and then decline. This phenomenon is observed not only at the level of individual civilizations, but throughout the entire geological history of Earth. There are theories that assert that for millions of years, various cultures and societies have risen and fallen depending on external and internal factors. For instance, in ancient times, Mesopotamia, Egypt, and India experienced periods of flourishing due to geographical conditions and the development of agriculture, but soon faced challenges such as resource depletion and internal conflicts. A similar fate befell the Roman Empire, which reached the peak of its power only to crumble under the pressure of economic difficulties, barbarian invasions, and political instability. These cycles can be observed in more contemporary societies as well. For example, the Industrial Revolution in the 18th and 19th centuries led to rapid technological development, but also social changes and crises that could lay the groundwork. Some scholars believe that periodic technological leaps and their consequences may be part of a larger historical cycle in which each new wave of progress brings both opportunities and risks. Therefore, while we can observe progress and seem to have reached new heights, it is important to remember that each technological boom can lead to its own decline, making human history resemble a biological cycle of life. An example of such a phenomenon is the disappearance of civilizations like the Maya, which reached a high level of development but then declined due to changes in climate and social conflicts. The concept of forgotten knowledge suggests that crucial information about past civilizations could have been lost due to various factors, such as global catastrophes, migrations, and cultural collapses. For instance, natural disasters like earthquakes or volcanic eruptions could have wiped out entire cities, as happened with Pompeii in the 21st year of our era. These migrations also played a role. When peoples left their lands in search of better living conditions, they often left behind their cultural achievements, including technologies, art, and written traditions. For example, Greeks and Romans, when they arrived at new territories, often did not preserve local knowledge and practices, leading to their loss. As a result, accumulated experience and achievements disappeared, creating a void in the historical consciousness of future generations. Considering that many peoples left only oral traditions, the true depth of their knowledge about the world often remains inaccessible for research. These losses shape a complex picture of our understanding of history, as each lost piece of knowledge could be a key to solving cultural and scientific mysteries of the past. In archaeological finds, such as clay tablets from Mesopotamia, one can see how much information was once available but is now lost to time. Cosmic consciousness is a concept that encompasses the understanding of humans as part of a broader universe, emphasizing the interconnectedness between all forms of life and matter. This state of awareness includes the realization that there is something greater than just individual experience, and that each person contributes to the collective flow of life and energy. From the perspective of cosmic consciousness, the thoughts, feelings, and actions of each of us have significance not only on a personal level, but also on the scale of the entire universe. Applying this concept to daily life can lead to a deeper understanding of one's actions and their consequences, as well as the development of a sense of responsibility for the planet and society. There are many interpretations of cosmic consciousness, ranging from scientific to more metaphysical, but the essence remains unchanged. We are not isolated beings, but part of a unified cosmic whole. For instance, some researchers claim that this state of consciousness can be achieved through meditation or deep self-awareness, opening new horizons for understanding the interaction between humans and the world around them. In this context, it is important to note that cosmic consciousness can serve as a foundation for a more sustainable and mindful approach to life, which is particularly relevant in the era of global changes and challenges. Specifically, it encourages us to consider how we can use our knowledge and resources to improve life not only for ourselves, but also for future generations. There is a belief that such consciousness can help address environmental and social issues, emphasizing the need for collective efforts to achieve positive changes. Studies show that people with developed cosmic consciousness are more likely to care for nature and participate in community initiatives. The hypothesis of panspermia suggests that life on Earth could have originated not on our planet, but rather was brought in from space. Proponents of this theory argue that meteoroids or comets could have carried tiny organisms or their precursors, which then adapted to Earth's conditions. This idea sparks intriguing speculations about possible ancient intelligent beings that might exist in other corners of the universe. For instance, if life on Earth indeed originated from extraterrestrial organisms, it could imply that similar beings could have developed on other planets, creating their own civilizations. Scientific research indicates that some microorganisms can survive in extreme conditions, including radiation and the vacuum of space, highlighting the possibility of their interstellar travel. Additionally, findings of organic molecules on comets and other celestial bodies support the hypothesis that the elements necessary for life's emergence could be widespread throughout the galaxy. There are also ideas that such ancient beings might have left traces of their existence on Earth, such as artifacts or mysterious structures that we still cannot explain. These assumptions raise numerous questions about our place in the cosmos and how truly alone we are in this vast universe. Scientific research continues, and each new discovery about the composition of meteoroids only fuels interest in this topic, confirming that life on Earth might be just one chapter in the book of the universe. In recent years, experiments have shown that some organisms can survive in the conditions of space, further supporting the possibility of their travel through the cosmos. The concept of cosmic intelligence posits a hypothetical form of consciousness that may exist in various corners of the universe. This is not merely an abstraction, but an idea that intelligence can manifest in diverse material forms across different planets, adapting to their environmental conditions. For instance, it is proposed that on planets with high temperatures, intelligence might develop in forms reminiscent of Earth's extremophiles, such as thermophilic bacteria. Meanwhile, on watery worlds like Europa, Jupiter's moon, intelligence could take forms similar to marine creatures capable of complex interaction and communication. This concept also suggests that cosmic intelligence is not limited to biological forms. It could exist in crystalline structures gases, or even pure energy, challenging traditional notions of consciousness and life. There are theories that such a form of intelligence could have evolved in a manner analogous to Earth's evolution, but under entirely different initial conditions. These hypotheses open new horizons for understanding intelligence and its potential manifestations, raising numerous questions about how these entities might interact with one another and their environment. For example, if cosmic intelligence could exchange information via sound waves or electromagnetic pulses, this could fundamentally alter our understanding of communication within interstellar civilizations. Notably, some researchers emphasize that such intelligences might have entirely different perceptions of time and space, making their existence even more enigmatic. In this context, the possibility of cosmic intelligence existing and being studied could aid in the search for extraterrestrial life and expand our understanding of the very nature of consciousness, adding another layer to our comprehension of the universe. There are even hypotheses that such intelligences could be capable of collective thought, forming a unified consciousness that spans entire star systems. This phenomenon involves two or more particles becoming linked, such that a change in the state of one particle instantaneously affects the state of the other, regardless of the distance between them. Information transfer occurs without the use of traditional communication technologies like radio waves or lasers. For instance, this property of quantum entanglement raises numerous questions about the nature of time and space, as well as the possibility of using this phenomenon to create new forms of communication between civilizations. Scientists are already exploring ideas about how quantum entanglement could be used for information transfer, but so far this remains at the theoretical level. An example of this is an experiment conducted in 2020, where researchers were able to demonstrate entanglement of particles over a distance of more than 100 kilometers. This confirms that quantum entanglement can serve as a foundation for creating entirely new ways of interaction between intelligent beings, possibly even without the need for physical information transfer through space. However, nevertheless, the very existence of such mechanisms challenges traditional notions of communication in space, opening new avenues for research in astrophysics and quantum mechanics. The question of ancient civilizations provokes numerous reflections on not only their way of life and achievements, but also on the profound philosophical aspects that defined their existence. Each civilization formed its own views on the world, which were reflected in their religion, myths, and art. For example, the Sumerians created myths about the creation of the world, which explained the origin of humanity and its purpose. In ancient Egypt, pharaohs were considered divine beings, emphasizing the importance of religious beliefs in society. It is important to understand that ancient civilizations were not isolated phenomena, but part of a broader process of human evolution that continues to this day. Their legacy shaped not only cultural and technological aspects, but also the foundations of human thought and perception of the world. Each of these civilizations left its unique mark, which can be traced in archaeological finds and written sources. For example, in India, the Vedic literature contains philosophical reflections on life, while in China, the works of Confucius discuss social relations and moral norms. These cultural layers form a complex fabric of human history, where each thread represents a unique experience and knowledge. A distinctive feature of ancient civilizations is their pursuit of harmony with the surrounding world, which is evident in their architecture, art, and daily life. For example, in Mesoamerica, architecture was often connected with astronomical phenomena, highlighting the importance of astronomy in their culture. In this context, the philosophy of ancient civilizations becomes an important tool for understanding their values and worldviews, which in turn influence their choices and actions. The questions they raised remain relevant today, as we face new challenges that require deep analysis. In this context, the study of ancient civilizations can help us better understand how humanity adapted to changes and how we can use this experience to solve contemporary problems. The exploration of these questions opens new horizons for understanding not only the past, but also the future of humanity. It is significant that many of these philosophical ideas continue to exist in various forms today, highlighting their universality and importance. For example, ideas about justice and harmony with nature are reflected in modern environmental movements and the search for sustainable development. These parallels show that ancient civilizations did not simply remain in the past, but continue to influence our perception of the world. Thus, the history of humanity becomes a complex and multi-layered canvas, where each civilization adds its unique note to the overall symphony of human experience. In this context, the study of ancient texts and artifacts provides a key to understanding how our ancestors perceived their reality, which can help us gain a deeper understanding of our own essence and place in the world. When we contemplate the hypothesis of multiple origins and extinctions of intelligent life on Earth, existential questions arise that challenge our understanding of the very nature of existence. What if we can ask, what forms of life existed before us and why did they disappear? Were they capable of creating complex civilizations like ours, or were their existences brief and insignificant? If intelligent life could arise and vanish, how does this affect our understanding of time and progress? It is important to consider that each time intelligent life disappears, it may take with it knowledge and achievements that could enrich the future. For instance, civilizations like Atlantis or earlier cultures that left mysterious traces could be evidence that we are not the only ones who have tried to understand and change the world around us. What were the causes of their disappearance? They could have been climate changes, ecological catastrophes, or internal conflicts that undermined the foundations of their existence. It is also worth considering how our own existence and our desire for knowledge are an integral part of this cycle. This question leads us to ponder what awaits us. Can we avoid the fate of those who came before us, or will we also become part of this endless cycle? In the context of such reflections, it is particularly interesting to consider how modern technologies and scientific achievements can influence our fate. For example, the exploration of space and the colonization of other planets can open new horizons for humanity, but also pose threats to ecosystems and raise ethical questions about our right to interfere with other worlds. These existential reflections on life and its diversity force us to look at our place in the universe from a new perspective, and each question opens doors to new hypotheses and scenarios. Scientists study the traces of life that may have existed millions of years ago and find fossils that may hold the key to solving these mysteries. For example, in the Chinese basin, remains of organisms were found that could be the predecessors of modern forms of life. This loneliness leaves a certain imprint on our self-perception and understanding of our place in the cosmos. If scientists were to find traces of ancient non-human civilizations, this could fundamentally change our perception. For instance, the discovery of artifacts on other planets or even on the Moon could confirm that intelligent beings once existed outside Earth and possibly developed in completely different conditions. This discovery could not only alter our scientific theories but also influence our philosophical and cultural views. People would begin to ask questions about how such civilizations could have existed, what technologies they used, and why they disappeared. In this context, the discovery of ancient civilizations would not just be a scientific fact, but a genuine cultural shock, forcing us to reevaluate many aspects of our lives. For example, if it were found that other beings could have left their traces on planets, this would make us rethink our role as custodians of Earth and potential explorers of other worlds. Such discoveries would not only open new horizons in space research, but also change our views of ourselves, making us ponder who we really are in the vast expanse of the universe. Currently, searches for exoplanets continue, and astronomers are discovering more and more potentially habitable worlds, which fuels the hope that one day we may find not only traces, but also beings who could tell us their story. The cosmic heritage we inherit poses a multitude of philosophical questions to contemporary humanity. We are not only the descendants of ancient civilizations that left their mark on Earth, but also potential bearers of intelligence capable of continuing the line of life that existed long before us. How will we approach this responsibility? This is not just a question of how to preserve nature or culture, but also of how to utilize the knowledge and technologies we have acquired. Our ability to self-preserve depends on how we perceive our place in the universe and how we act to avoid repeating the fate of those who came before us. We must realize that what is at stake is not only our survival, but also the fate of potential future generations who may inherit our earthly experience and cosmic heritage. Considering all this, it is also important to remember that our attitude towards other forms of life, whether on Earth or beyond it, should be based on respect and understanding. In this context, philosophical reflections on heritage and responsibility take on new meaning, considering how we can contribute to the general cosmic heritage. The first steps in this direction have already been taken. Projects for the search of extraterrestrial life are actively being developed, and scientific research is opening new horizons for understanding life in all its forms. For example, the Kepler mission discovered more than 2,000 exoplanets, opening new possibilities for studying potential forms of life beyond Earth. When we discuss the possibility of non-human forms of intelligence existing in the distant past of Earth, we encounter metaphysical questions concerning the nature of consciousness and reason. How do we define intelligence? Can we perceive it through the prism of human experience alone? For instance, ancient civilizations like the Maya or Sumerians left behind enigmatic monuments and texts that may indicate a high level of understanding of the surrounding world, but we cannot precisely determine how they perceived their reality. Some researchers suggest that there could have been forms of intelligence different from ours, employing different methods of information perception and interaction with the environment. This leads us to ponder, can intelligence take various forms, and if so, what are its criteria? Some scientists propose that such organisms might exhibit certain forms of social structure and communication, which also challenges our notions of what it means to be a rational being. Comparing intelligence across various animal species, from dolphins to sparrows, also raises the question of how we evaluate the complexity and significance of different forms of thought. We may be constrained by our human criteria and standards. Research shows that many animals are capable of complex social interactions and tool use, which may indicate the presence of a certain level of consciousness. In this context, it is important to note that the concept of intelligence is not static and can vary depending on the conditions of existence. This necessitates a re-evaluation of our traditional model of intelligence, considering that over millions of years on Earth, there could have been beings with unique forms of consciousness that we currently cannot comprehend. Taking all this into account, contemplation of metaphysical questions about consciousness and intelligence becomes an integral part of our understanding of both the past and potential future contacts with non-human forms of life. Scientific experiments, such as research on dolphins, demonstrate that they can use sound communication to exchange complex information, indicating the presence of highly developed intelligence. Ethical aspects of searching for and studying traces of ancient civilizations are becoming increasingly relevant in our society, where respect for cultural heritage and the preservation of historical truth are of paramount importance. When archaeologists work on excavations, they often encounter questions about how to handle artifacts and remains found at ancient settlements. For instance, if burials are discovered, it is crucial to consider that these are not just objects of study, but the final resting places of people who once lived and had their own cultural practices. In some cases, such as findings in Latin America, indigenous communities demand that their ancestors not be disturbed and that their cultural heritage remain untouched. This raises the question of who has the right to study and interpret history. Can it only be those who share the same cultural identity, or can researchers from other cultures also contribute? Archaeological finds often become the subject of disputes when certain groups feel their rights to the heritage are not being recognized. For example, cases where artifacts are taken to other countries and cause protests from local communities clearly demonstrate the importance of ethics in archaeology. It is moreover, when studying extinct intelligent species such as Neanderthals, it is necessary to consider that they were also part of the ecosystem, and their extinction may be linked to human activity. Genetic studies show that modern humans and Neanderthals had interactions, which raises the question of how we should perceive our common heritage. These aspects require researchers not only to be scientifically accurate, but also to have a deep respect for what they are studying. Respect for cultural heritage and understanding the context of finds are the cornerstones of an ethical approach in archaeology. It is important to remember that each find is not only a scientific interest, but also a part of someone's history, emphasizing the need for a responsible attitude towards the past. In this context, archaeologists should not only uncover new facts, but also be prepared to discuss the ethical questions related to their work. The concept of cosmic ethics raises intriguing questions about moral obligations between intelligent beings separated not only by vast distances but also by millennia. This idea is based on the assumption that in the future we may encounter other civilizations that may already exist or have existed in the past. For example, if we discover traces of ancient extraterrestrial life on other planets, the question arises, what ethical norms should we apply to these beings? Should we attempt to restore their culture or even interact with it? For instance, here, reflections on cosmic ethics can even lead to a rethinking of what it means to be an intelligent being in the context of a broader cosmic community, where every action has consequences. How can we ensure that we are not just researchers, but also protectors of cultures and civilizations that may be lost in the flow of time? It is important to note that these questions become particularly relevant in light of modern technologies that allow us to explore other planets and potentially make contact with extraterrestrial life forms. Planets like Mars may hide traces of past civilizations beneath their surfaces, and how we react to these discoveries will depend on our understanding of cosmic ethics. This understanding should be based on respect for histories that may be completely different from our own. For example, if we find remnants of intelligent life that existed millions of years ago, how will we treat these remnants? How can we ensure that our intervention does not disrupt their historical integrity? All these questions require us to adopt a new approach to ethics that takes into account not only our time, but also potential connections with other intelligent species. This raises important questions about how we can establish moral frameworks for interaction with other beings that may exist in other corners of the universe. In this context, the study of ancient civilizations and their cultures becomes not just an archaeological question, but a part of a broader picture where ethics and moral obligations extend beyond our own time and space. For instance, in different corners of the world, traditional crafts, oral history, or rituals are preserved and adapted to modern conditions, becoming an essential part of the cultural code. It is important to note that heritage for the future is not limited to material aspects. It also includes philosophical and moral ideas that can serve as a foundation for the formation of social values. Therefore, when we talk about heritage, we are referring to a complex of factors that influence the perception and development of culture. This is not just a collection of stories and artifacts. It is a living fabric that connects the past and the future. For example, some peoples restore ancient rituals to maintain a connection with their ancestors, while others seek a balance between traditions and modern challenges. In this context, heritage becomes an integral part of the dialogue about how we see ourselves and how we want to be seen in the future. It is not only important to preserve this heritage, but also to understand how it can be made relevant in the present, which requires careful analysis and a thoughtful approach. Numerous archives stored in museums and libraries become key sources for researchers who strive to understand how our past shapes the present and influences the future. In this context, for example, collections of ancient texts and artifacts open doors to a world where each discovery can tell its own story and contribute to a broader understanding of human civilization. Archaeologists find evidence of changes in cultural practices that have occurred as a result of contacts between different peoples, opening new horizons for research. One striking example is the Millennium Message Project, initiated in the United States at the end of the 20th century, which included ideas on how to transmit information about our civilization for thousands of years. Researchers proposed various formats, such as burying metallic containers with recordings and images that were meant to survive for a long time. It is interesting to note that even in ancient civilizations like the Sumerians or Egyptians, people left messages on clay tablets or in the form of hieroglyphs on the walls of temples. These inscriptions served not only as documentation of events, but also as an attempt to establish a connection with future generations. For instance, in Mesopotamia, cuneiform records were created that contained not only administrative records, but also myths that reflected the cultural values of the time. Another example is the Egyptian pyramids, which carried not only the burials of pharaohs, but also texts intended to help them in the afterlife. Modern research shows that such messages can be not only historical documents, but also forms of communication with intelligent beings that may appear on Earth after the disappearance of humanity. In this context, the question arises, what messages will we leave, and will they be understood by those who come after us? Some scientists even propose creating time capsules with samples of our culture, which will be buried at depth to be discovered by future archaeologists. These ideas raise interesting questions about how we perceive our heritage and what exactly we want to pass on. Considering that our planet is undergoing changes due to human activity, long-term messages are becoming not just a concept, but a necessity for preserving information about our civilization for future generations. For example, in the 21st century, ideas emerged about creating digital archives that would be stored in safe places to preserve knowledge about our time. Deep time information repositories represent a concept that could play a pivotal role in preserving knowledge over millions of years. One example of such repositories is the Seed of Life project, which proposes storing genetic information about all known plant and animal species in specialized underground repositories. Additionally, some scientific circles discuss the idea of creating time capsules containing records of scientific discoveries, cultural achievements, and historical events. For example, such a capsule might include information about technology, art, and language to enable future civilizations to understand how life on Earth has evolved. The use of time-resistant materials, such as quartz or special polymers, which can preserve information in the form of data on magnetic or optical media, is also considered. These materials could maintain information in a stable state for millions of years, making them ideal for such purposes. A crucial aspect is the creation of a system to protect against external factors, such as radiation or physical damage, to ensure the integrity of the repositories over a long period. Such repositories could serve as a bridge between different future civilizations, facilitating dialogue between them over millions of years. It is also interesting that researchers discuss the possibility of creating a language of the future, which would be understandable regardless of cultural differences, to ensure access to information for any civilizations that might discover it. For instance, universal symbols or physical constants, which have the same meaning for all rational beings, could be used as a universal language. Thus, deep time information repositories could become not just archives but genuine time capsules that preserve our heritage and knowledge for future generations. In this context, the Arctic Repository Project, located on the archipelago of Svalbard, stands out, which is designed to store seeds of plants from around the world. The concept of cosmic altruism is based on the idea that highly advanced civilizations may deliberately leave knowledge and technologies for future intelligent species, even knowing that they will never encounter them. This is a kind of philosophy that assumes that advanced societies with significant technological achievements can consider their responsibility not only to themselves, but also to potential forms of life that may arise in the future. Within this framework, it is assumed that such civilizations could create information repositories similar to the Arctic repository to pass on their achievements and experiences. This could include not only scientific knowledge but also cultural artifacts, art, technologies, and even moral principles. For instance, future generations. This concept raises numerous questions about the nature of life and intelligence, about how civilizations can interact, even when they are at great distances from each other. Some research indicates that such thoughts about cosmic altruism are not just fantasies, but real possibilities for humanity if it ever reaches a level of development sufficient for interstellar travel. The question of the existence of ancient prehistoric civilizations that may have preceded us remains open and is a subject of much debate among researchers. Discoveries such as Stonehenge in England or the megalithic structures in India challenge traditional views on the development of human culture. These artifacts compel us to reevaluate our history and our place in time and space, regardless of whether we were the first technological civilization on Earth or one of many. The fact remains that we bear responsibility for preserving life and intelligence on our planet. Humanity must consider its actions and their consequences, for our epoch is but a fleeting moment in the endless stream of time. As night envelops the world, it is a time to ponder the infinite possibilities that lie within the depths of time and space. As we drift off to sleep, we can allow ourselves to reflect on what lies ahead and the mysteries yet to be revealed. For instance,